Welcome to this explanatory video on the dynamic grid. The goal of this work is to allow for parameter variations in musical instrument simulations which are physically impossible. So say that you have a violin and you want to virtually grow it to a cello, for example, by enlarging the body, lengthening the strings, etc. This is one example of a physically impossible parameter variation. And this idea we want to apply to finite difference time domain methods, which is one of many methods to implement virtual musical instruments. And these methods essentially discretize partial differential equations, which are continuous, to discrete time to a finite difference time domain scheme. And you can see here the example of the 1D wave equation with wave speed c and state q. So continuous space is subdivided into n equally sized intervals here. And also you can see once we run the simulation that time is also discretized here. So if we take a closer look at this grid in space that we now created, we can call the distance between two neighboring grid points, we can call that h, and h needs to abide this stability condition in the case of the 1D wave equation, where it needs to be larger than or equal to the wave speed times the time step, which is 1 over the sample rate. For simplicity, we will now set it equal to the wave speed times the time step. So we can now see that if we would like to change the wave speed in real time, for example, from a large wave speed to a smaller wave speed, the grid spacing will also change, and therefore also the amount of grid points that we can use to describe our system with optimal quality. So you can see that this might lead to some issues to go from one grid configuration to another, because the grid is highly reliant on the parameters of the system. So this is where the dynamic grid comes in. And the way we start here is to take our original system, our original discrete grid, and subdivide it into two subsystems. In this case, we subdivide our original system Q into subsystems V and W. And in the middle here, they overlap, and we can zoom in here, where we can expand the schemes, and more details about this are in the paper, by the way. Where we can now see if we expand here, we need neighboring grid points for each of these systems, which are undefined. So they are outside of our defined range of calculation, and we call these virtual grid points. And as a starting point, we can set the values of these virtual grid points equal to a point in the opposite system. And this actually creates behavior which is identical to that of the original system. But what now if we want to change parameters? Say we want to decrease the wave speed in our model. This then decreases the grid spacing h according to this equation that we saw before. So the way that we implement this is to fix the boundaries of our system and move all the other grid points towards their respective boundaries as the grid spacing decreases. So as follows. If we zoom in to how this would look with these virtual grid points that we just talked about, these no longer overlap in space with a point of the neighboring system. So we need to find alternative definitions. And what works very well is to use quadratic interpolation. So using neighboring grid points in order to calculate the values of these virtual ones. And these are the definitions for these, where the interpolator here is calculated using alpha, where alpha is kind of how many times does the grid spacing fit in between these 2 points. And this will always be between 0 and 1. If we then further decrease the wave speed, we need to start adding grid points. And this is done through cubic interpolation. So we can add a grid point. And if we increase the wave speed, on the other hand, we need to remove grid points. And this is done by simple removal or simple deletion of these grid points. All right, so now we need to, in order to apply this to more complex systems, we need to write this entire method in matrix form. So we can annotate these points here, starting with V0 here, V1, etc., and here W0, W1, etc., and concatenate these into a large vector, which is called U. And you can see that I excluded the boundaries here, as they will always be fixed in their state or in their displacement. This is of size m, and this is also varying with time, because we can add and remove points. And we can, using this vector, we can end up with this general form, where u at the next time step can be calculated by u at the current and u at the previous time step. And multiplied onto these vectors are matrices A, B, and C, which are square matrices of size m times n. If we remember the dynamic grid method here, we can also include this into an already existing matrix, which we have for the 1D wave equation, as follows. So we can simply add these interpolator terms to the matrix we already have. And details, again, are in the paper. So to recap, we start with our finite difference time domain scheme, in this case the 1D wave equation. We can split the system into two subsystems and write this in matrix form to get this general form. And in the case of the 1D wave equation, these matrices are as follows. So we have an identity matrix of the same size as U, but then a matrix. And here we see this matrix that we just created, including the dynamic grid method. So now that we have established this, we can apply it to a more complex system, such as the stiff string. Again, we can take our finite difference scheme, split the system, and end up with this matrix form, where A, B, and C are now defined as follows. And this is a lot of stuff, but the most important takeaway here is this D 4 times X matrix, which, when we use fixed boundaries, so simply supported boundaries for the stiff string, we can simply multiply this dxx matrix that we created with the dynamic grid method, multiply that onto itself to get this matrix. And we can listen to a sound example here, where we vary some parameters from being a normal string to an octave up, to something that sounds like a vibraphone, and finally to something that sounds like a marimba. And this is all done, this can be all done in real time. And between these settings is about, like, one setting can be 15 grid points and one setting can be more than 100 grid points. So you can hear that this addition and removal of grid points can be very smooth, actually. All right, so we can also move this method to 2D systems. So if we now have a system Q, which is two-dimensional, we now need to split it into 4 different subsystems rather than 2. And we can also move these points apart and concatenate all of these in one large vector. And again, details are in the paper about this. And this can be, this is size M2. And then we can use this in the end for our matrix form. And now, starting with the 2D wave equation, which is described as follows, we can split the system in 4 parts now and end up with this matrix form that we saw before. And now A, B, and C are defined as follows, where here now we have our matrix, including the dynamic grid method, but it consists of this Kronecker sum of dyy, which is the same as dxx, but then in the y direction of the 2 dimensions, and dxx, which we've seen before. And finally, we can apply this also to a more complex 2-dimensional system, which is the thin plate, defined or described by this following scheme. We can split the system into 4 parts again, and finally get this matrix form, where A, B, and C are now defined as follows. And here again, we can multiply this second order matrix by itself to get this 4th order operator matrix. And this can sound like so. So here we change the length to be longer, the plate's length is longer, and then it's shorter again with these two parameter variation ranges. Thank you. I hope this made a bit of sense, and feel free to contact me if you have any questions.